So as most of us know, like these days, we are talking about this big data analytics. There is a lot of data is being generated, and everybody is trying to make sense out of this data. I think that is the overall goal. Now, where the data is being generated. So this just shows like a lot of, especially on the internet side, if you see like starting from the web pages to clickers to emails, all different kinds of ways data is being generated and people want to analyze those data. If you just take only one of these, let's say installed apps, if you see the trend over the years, like you will see that just the number of apps have been steadily increasing. Okay, so now you can see that the number of apps have been increasing, the data associated with it is also continuing to increase. Now that is not just the internet data, but we also see the similar kind of things in the traditional HPC side. I mean, so as we are talking about the petascale systems, exascale systems, people are trying to do not just process the data, but also manage, analyze, and visualize the data. And if you take some examples like climate modeling, combustion, fusion, astrophysics, bioinformatics, so typically a scientist or engineer tries to simulate these, run the job, then you dump the data on the parallel storage systems, collect the data, move the experimental data to some analysis site, and also do visual analytics. So these are the kind of traditional things we also see from the scientific side. So then the question is, what are available currently to process this kind of data? So of course there are a lot of different tools are available or software structure. Most common are Hadoop, Spark, and I'll also talk a little bit about the Memcache D. These are the three kind of things. I'll just show some detailed examples. I'm sure, I think most of you must be familiar with Hadoop. How many of you have used Hadoop? Okay, some of them Spark, okay, Memcache D. Not many, okay? But actually all of us use Memcache D in an indirect manner. I'll give some example, okay? So this is the very standard Hadoop. Many of you must be familiar. If not, there are different components here. The main thing is the Hadoop distributed file system, where we actually store the data. Then we have the MapReduce, that is the computation mode, and typically it gets done in a batch mode. Then there is an HBase, which is the query, and then there is the RPC, which is interprocess communication, which takes place between these components. And this model has been used over the period of time to scale. But what we see basically, especially when we are trying to process large amount of data, there could be a lot of communication bottlenecks. And that's what exactly I want to highlight later on, how we can accelerate that part using these high performance, all these InfiniBand and the modern networks. Now this is the Memcache D. Before going down into the details, let me give an example. You can correlate in real life. Let's say we all travel, most of the people here, and we buy tickets. So how many times, let's say you have chosen or searched, might be from New York to San Francisco, you did some search 2 months back to come to this conference, and you found out a very attractive price. Then you clicked it, then you suddenly get an error message saying, sorry, that ticket is not available. Have you seen a message like this? Okay? If so, you have used Memcache D. Okay? That is a very clear thing. So what has happened is the data centers actually use Memcache D. What it means that the servers, they take some memory from different nodes and collect a distributed caching layer or prepare a distributed caching layer. And what it does, it is a general purpose, and it typically caches database queries or results of some of the previous calls. So might be what had happened before you, somebody else tried to do a similar search from New York to San Francisco, and that price was cached there. Okay? And then when you tried to do the search, that result came out. But obviously this is a little bit misleading, but there is a rule behind it. Why these guys are doing it, that depends on how we actually purchase the tickets. How many times you typically do a search and then buy a ticket? Is it 1:1? 5:1? 10:1? Might be some people go 50:1. Okay? So we always don't do, like we do a lot of search, but we don't actually do the transaction. So to provide a very good high throughput transaction, so this is the kind of components which have been designed so that they can give you some information. It is not like always you don't have to go to the end database, because the database load will be very high. if each and every query goes there. So this is a big component which is used in all multi-tier data centers, and over the years, as the data centers are trying to grow, people are also trying to see how to build larger and larger Memcache D. So typically in a multi-tier data center, this is how you will see, like this is from the internet. We might be doing some searching tickets or buying something from Amazon.com. So typically you see Memcache D here, HBase here, and in the back end here, we see MapReduce, Spark, HDFS, those kind of components are there. Now almost here everybody knows about InfiniBand. I mean, this has been, the technology has been there for almost like last 16 years. And these days we are able to go to these kind of very good numbers. I showed some of these numbers yesterday, like latency of 1 microsecond, bandwidth of almost 100 gigabits per second. And the third parameter, which we will also see, is the low CPU utilization. And especially the RDMA, which is the remote DMA technology, allows us to actually reduce the CPU overhead. So that has actually led to all these different kinds of operation, RDMA read-write, atomic operations, and this has led to big challenges in designing what we are seeing today, HPC clusters, file systems, cloud computing systems, grid computing systems, etc. So in that context, people have been asking a lot of questions, and we also asked the similar kind of questions like a few years back based on our experience with the MapReduce project, which I indicated yesterday, like for 15 years we have been working there. So we started asking questions saying, if this big data is becoming very common, what are the kind of bottlenecks in doing this kind of processing in the Hadoop stack or Spark or Memcache D? And can these bottlenecks be alleviated by taking advantage of the HPC technologies? And especially, can the RDMA-based operations be used here? And at the same time, as many of us know, like HPC clusters use like parallel file systems like Lustre, GPFS. Can we also take advantage of that? And if we can do all these things, how much performance benefits we can actually extract using the same hardware? But if we redesign the software stacks, can we get more and more performance out of this? And at the same time, how also we can try to do the benchmarking. So these are some of the fundamental questions in my group. Actually, we asked around like 3-4 years back when we started the research along these directions. And broadly, we also asked the thing saying HPC is there and big data is there. Instead of they going in a separate direction, can they actually converge so that we can actually use the similar kind of solutions on both the sides? So just like yesterday I showed a stack, similar kind of issues also happen here. If we want to design a high-performance communication and I/O libraries, we have the commodity computing systems, multi-core, many-core, networking technologies, storage technologies. So these are the top levels. We have the big data. So all the Hadoop, MapReduce, all the components lie here. And traditionally what has happened, all these are written with sockets. So that is the fundamental thing which we'll try to address. And sockets, as you know, is a very generic network programming. It can run over Ethernet. It can also run over InfiniBand using the IP over IB mode. Christian made a comment about that in the last talk. So you can always run a sockets-based application. But gradually we'll see that that has some overhead. And the question is, can we alleviate that kind of overhead? So here, these are, again, the different kinds of communication and I/O library components. But before we jumped into that, we started asking the fundamental questions that can we take from the sockets to some other protocols, like RDMA. And if we can do that, then what happens is the network protocols become much more faster. Then it leads to the second question is that can we revisit the overall architecture or the upper level designs, because these stacks were designed with slow network in mind, slow protocols in mind. So now if we can accelerate those, then there are more opportunities to explore at the top level, and then we can combine the benefits to see even better benefits. So that was the kind of questions we asked. This is the very high level. It is trying to provide the pictorial view. That means, let's say this is a big data application or middleware was running on sockets. So the question was, can we bring a new design which can directly run over verbs? So that is the the lowest layer on the InfiniBand stack or the Rocky, or you can think of IORP. So all those layers, that is the lowest RDMA layer, and can we directly design at that layer? So that was the first problem we asked. So we have done a lot of research. I'll show you all the results. But just like the MapReduce project, as the results started coming, people wanted to use it. So we have actually started putting this together. And these are public releases. You should be able to download. So if you just go to this site, it's called HighPerformance Big Data. And we have a lot of distributions. And these are all available for InfiniBand and Rocky. We started with RDMA for Apache Hadoop 1.x. But then last year and all, Hadoop 2.x became very common. We moved there. Then recently, we have also released the RDMA for Apache Spark. And especially in the Hadoop side, we also have integrated package. We also have plugin packages. And especially the plugin packages for Hortonworks and Apache, so that if you already have an installation, you don't have to totally reinstall everything. So you can just take our plugin and then put it there, and then it will replace the sockets-based protocols to the RDMA-based protocols. We also have the RDMA for Memcache D, and also, just like the MPI project, we also have been also pushing a lot of benchmarks, micro benchmarks, so that people can actually evaluate not only our stacks, everybody else's stacks, and then see where the benefits are coming from. And this has been like 18 months. We started making this available to the community, and so far you can see like around 145 organizations are using it. We have very close to 15,000 downloads from our site itself. The packages people are using it. So let me go into a little bit of detail. So this is the Apache Hadoop 2.x. So here what we have done is, I'll go into the much more technical details in the next few slides. So we call it a heterogeneous storage, so that we have different kinds of mode. We can run it on SSDs, we can run it with hard disk, we can run it over Lustre, we can also run it in memory or in any combination of these. So that is like the new kind of HDFS designs. Then of course we have the similar kind of RDMA enhanced MapReduce together with also Lustre or local disk. We also have RDMA enhanced RPC, and we also provide an interface with the typical job scheduler. Let's say you have the HPC systems with PBS running or Slurm is running. We have interface so that directly it runs using the existing HPC framework. So let me just touch few of these things. We may not have time to go over all these things. So I'll start with the HDFS and MapReduce, then go into Spark, some of the Memcache D, and now we have some of the advanced stuff like even combining HDFS with Memcache D, those kind of stuff, designs we are working on. So this is a very high-level picture. We started this work. This was the first. We tried to ask the question how we can enhance HDFS with RDMA. So this paper was published in Supercomputing 2012, almost three years back. So the whole idea was that typically if you take a look at the HDFS, these are all written with Java. These are not C code. Okay? And then what runs here is the Java native interface, JNI. And mostly in the HDFS, many of you might be knowing, the write operation is the most time consuming because it makes replication. Okay? So that is the part we wanted to address. So instead of the JNI running over with like the sockets, we tried to put it over the verbs. And everything else we kept unchanged. Okay? And in all these designs, we also have not changed any of the APIs. APIs remains the same. From the top level, if somebody is using HDFS or MapReduce, Memcache D, API remains the same. So we are not forcing anybody, except the very end, I'll talk about Memcache D. We are taking some very futuristic look. But otherwise, if you have any other applications, our library should just transparently run. You don't need any changes there. So then this is the Triple H heterogeneous storage. So I mentioned about this. So here you can say all different storages we can combine, the hard disk, SSDs, even the RAM disk, so that you can run HDFS in memory, also Lustre. Then there are different policies to utilize these heterogeneous storage devices. You can specify saying, okay, I want 50% of data to be on the SSDs, 30% in the RAM disk, remaining 20% in the hard disk. So there are all different configuration parameters. You can do some kind of hybrid replication. And similar kind of things we have done also for MapReduce. The MapReduce inside, we not only changed it to the basic RDMA based shuffle, because in the MapReduce, the shuffle time, that is the most time consuming time. So instead of doing it in a two-sided operation over sockets, we have changed it to like a one-sided RDMA based things. We have also done some prefetching, caching, and at the same time, we We have also done some in-memory merge, advanced overlapping. So a lot of techniques have gone in, and those techniques are all available in the published papers. I'll not have time to go over it. But let's take a look at some of the numbers. So if you download our stack, these are the kind of numbers you will see. There are some standard benchmarks. Those who are familiar in the Hadoop community might be knowing this, like random writer, TerraZen. So this number is taken on the tag stampede system. It is an InfiniBand FDR. And here it says like a random writer. So the orange line is the IP over IB. That means the existing stack is running with sockets over InfiniBand. And when it is running over InfiniBand, it's IP over IB. And this is the red line. That is the red bars. Those are our RDMA-based designs. So here you can see that same hardware, just by changing the software as the data size is increasing, we can, the overall execution time of the random writer, we can reduce by a factor of 3. Okay? Where you can get a 3x reduction in the time here. Similar kind of things you see also TerraZen by a factor of 4 here. This is the sort and TerraSort. These are the many common applications get used. So here you will see like you can cut it by half. Again, the same hardware, we are not changing anything, it's just the software. We are able to speed it up. And then similarly, this side also, TerraSort with single SDD, we are able to reduce by, again, 44%. Okay? And so then we went into some of the applications. So there are some applications, especially from bioinformatics. Some of you might be familiar with a cloud burst. Then there is a MRMS polygraph. So here again, we see like this, a pure HDFS. This is the luster-based solution. And here we can cut it down by 80%. And the cloud burst, we can give you like around 19% improvement for the end applications. So then some of you might be knowing like the Spark also has this equivalent kind of a file system which is called Tachyon. How many of you have heard of that? Okay. So Tachyon has this in-memory capability also. So then we tried to compare with our HDFS in-memory. How does it compare with Tachyon? So that's what you will see here. Like this is the HDFS, this is the Tachyon. Our H design is able to like here random writer, 200 gigabytes of nodes. This is our running over on the SDSC, San Diego Supercomputing Systems, the Gordon system. So here you can see that the HDFS, our H mode, is able to reduce the time by 47%. Here also it's on the sort, 200 gigabytes, we can give you like another 19% benefit. Okay? So now you can think of even like the Spark applications, you can run with our HDFS with the H mode. You don't need to go through the Tachyon, and then you will get these kind of benefits, what I'm trying to show here. So then some people also have been thinking that, let's say if you have only MapReduce application, okay, should you go through HDFS or can I directly use Luster? So let's say that you have some scientific applications you have written with MapReduce. You don't have to go through the entire Hadoop framework. You can totally skip it. Okay? Because a lot of HPC systems have the Luster, so the question is, can you directly interact with Luster? So we enable that mode. And so here it shows, again, there are different designs. We presented this in the last year's IPDPS. There are some Luster read-based shuffle, RDMA-based shuffle. You can also have hybrid. And internally, we have some dynamic adaptation here. And let me show some two set of numbers. So this is the taken on tag stampede. And tag stampede, if some of you know the architecture, each node also has a hard disk. So the question is, when you are running this MapReduce job, and when you are generating the intermediate data, do you put it on the local hard disk or you put it in the Luster? So there are two kinds of solutions can come. So here what I'm trying to show is the local disk is used as the intermediate data directory. So here we can see that almost half terabytes of sort in 64 nodes, we can cut it by almost half the time. It's like 44% reduction. And similarly here, 640 gigabytes of sort in 128 nodes, similar kind of things we can see, 48% improvement. And then on the other hand, if directly, let's say you have a cluster where you don't have the local disk, so everything can go to the Luster. Your intermediate data as well as the end data, of course, then there is a higher load on the Luster, and so benefits are a little bit smaller here. So here you can see like it is reduced by 34%, here reduced by 25% kind of things. So then let's moving on to Spark. This is the original design we presented at the Hot Interconnect 2014. So the broad idea here again, this is the Spark architecture. There are different kinds of shuffle. There is a NetShuffle here, Java and IOShuffle. So we actually took it instead of Java sockets. We changed the communication path so that it can actually go over the RDMA-based designs. And these are some of the numbers in the Spark literature. There are different kinds of benchmark, like one is called a sort by, group by. So here you can see 80% benefit compared to the IP over IP design. Okay, this is taken on the SDSC Comet, and there are different. All these details are there. This is a 1536 core experiments. It's a quite large job we are trying to run here. 80% benefit. Here is also around 57% benefit. Then these numbers are taken from SDSC Comet. These are the high bench sort and TerraSort. We are using again the standard benchmarks just to show the benefits. Compared to the IP over IV, you can see you can get with our RDMA-based Spark design, you can get around 38% benefit. Here, 15% benefit. So then there is another common benchmark which is called PageRank, and that is very common. Like just like on the web pages, you see the Google and all, they do all this page ranking. That means you get all the who is referring to which pages, and that's a PageRank is a very common algorithm there. And when we ran it on like a 768 cores on SDSC Comet, so you can make it faster by 37% time here and 43% time here. Once again, the key thing is hardware remains the same. We are not touching anything. It's just the pure softwares we have redesigned, which is trying to help you with this kind of acceleration. So then going to the Memcache D. Memcache D, again, as I showed in the architecture, in the beginning, the people were just taking memory from a set of nodes. And especially now, since SSDs have come, the next level of designs are trying to explore, saying, can we also combine SSDs? So that is kind of a hybrid design. So I'll show you the first, the basic design. So this is like a, this is taken over again on the tag Stampede. This is the FDR interconnect. So compared to the IP over IV, here you can see we can reduce the latency by almost 20x. Okay, by a factor of 20, we can reduce. And here we try to scale to almost 4K clients. It is a huge Memcache D. We try to simulate. And here we saw the transactions per second, we can give you the double. Okay, and that is a great benefit for any of the data centers deployers, because you are using the same hardware and you are trying to satisfy more number of users and give the reduced response time. I mean, that is the ideal thing. With the same hardware, you should be able to achieve or extract more. And then we have done some evaluations with different kinds of online data processing workload. So here it's like a MySQL slap load testing tools. So here we see that again the latency is reduced by 66%, and so that is like a query latency we are trying to reduce by 66%. The throughput we are able to improve by 69%. And then this is the hybrid design. So what we did is not only we take the memory, we also took the SSDs. Okay, so that you can have your entire capacity, we can significantly increase. But then there are different metrics you can see. Even though you have a large Memcache D, your data, whether it is fitting in the memory or not. Okay, so there could be some different trade-offs. So we wanted to make sure that first when we do the design, so this is like the IP over IP, and these are the two RDMA-based design. This is a pure memory, only we are aggregating the memory, whereas the hybrid is also we are combining the SSDs. And the first thing we proved that irrespective of like memory or hybrid, we are not hurting anything. When we go into the hybrid, we are not putting any additional penalty. But at the same time, compared to the IP over IP, here you can see that we can push the throughput again by factor of 2. So then we have performed a very detailed analysis with all different configurations like IP over IP memory, RDMA hybrid over SATA disk. Then now we are seeing this NVMe disks are coming up. And then this is the data which fits in memory, and this side is the data which doesn't fit in the memory. Okay, so we have done a very exhaustive analysis, and here we see that when data fits in the memory, our design gives around like a factor of 5 improvement over IP over IP. And then when data doesn't fit in the memory, we can actually go to the hybrid SSDs, and there we see still the factor of 2 or 2.5x improvement we can give compared to the IP over IP. So then very recently is the very latest work. This paper just got accepted 2 weeks back to be presented at IPDPS, this upcoming IPDPS. So what we're trying to do, these things we learned from our MPI side. You remember yesterday I talked a lot about non-blocking operations, non-blocking collectives. So we started looking at saying all these calls currently in the Memcache D, they're all blocking calls. So you initiate a query and then wait. So you are not effectively putting all the CPU and the network to stress. So we try to explore that, can we do some non-blocking API extensions? So this is like a futuristic look we are trying to provide, saying, okay, if we can go into the non-blocking API, what happens? And that's what we see. Like, so these are the kind of the earlier numbers I showed, like the default and some optimized, the blocking. And now if you do all this non-blocking and we have a complete solution ready, so then you will see you can even push the benefits by even significantly higher. Like you can get a 16x latency improvement and a 2.5x improvement. So through this, we are trying to show to the community, saying we need to totally rethink how these designs have been done. So moving forward, so then even we are taking one step further, like as many of you know, even in the HPC, a lot of discussion is going on burst buffers, how you can use the burst buffers to accelerate the I/O operations. The same thing we did here, like if you have a HPC Lustre environment, so then we said how we can have a Memcache D-based burst buffer system and then link it with the HDFS, okay, so that we can try to even exploit more. And this we presented last year. Similar kind of things you can see, like this is the yellow line, the yellow bar, where you can see that you can even effectively get another 40%, 48% benefit compared to what people are trying to do now. So these are some of the numbers, and through these things, what I want to also stress that there is a big need for micro benchmarks to guide these kind of designs. Okay, so what is happening, what we learned ourselves, and also the community is also experiencing the same problem, that when you do some design, you see some benefit. Let's say at the sort I showed you, like 44% benefit. But where that benefit is coming from, okay, from which layer, from which operations, okay, nobody knows. So that's what's the question, like what is happening at the lower layer, where the benefits are coming, which design is leading to benefits or bottlenecks, which components in the design needs to be changed. So in a pictorial manner, here you can say that currently people focus the benchmarks on the top, but then nobody knows what is happening here. When you start working on these layers, you need to have some benchmarks, okay? And the example I give, just like let's say you go to like a Ford or General Motors, people are designing the cars. If somebody is designing a tire, they have their own benchmarks. The tire team has their own benchmarks to design the best tire. Then the engine team has their own benchmarks. And then when you put it together, then only you run it on the road, okay, and see how much benefits we are seeing. So that kind of things are missing here, and there is also no correlation between these. And this experience also we found out from our MapReduce project, which I mentioned yesterday, like for 15 years. When we start, I remember in 2001, when we started pushing our new design, nobody knew how to compare different MPI stacks, okay? Like different operations, where the benefits are coming from. So in that context, we have introduced this OSU MPI micro benchmarks, OMB. Many of you must be familiar. And over last 16 years, this has become like an industry standard. These days, if you see all the biddings, all the bids, there is a line there saying, okay, refer the numbers using OMB. So we wanted to do similar kind of things here to the HighBD community, so that we can actually contribute back and let the community start looking at how to redesign these stuffs. So we have started working on this. So there is a set of HDFS benchmark, Memcache D benchmarks. These are actually available. You can download, and if you just want to evaluate multiple HDFS solution, irrespective if you're short or any of the higher level, you can use. These are real low-level benchmarks, and you can see how one HDFS compares with other HDFS. Similar things you can do Memcache D. We also have MapReduce, pure MapReduce benchmark. That means it doesn't depend on HDFS. Similarly, pure RPC benchmarks. So component by component, you can evaluate. And then these will be gradually released over a period of time. So to conclude this, what I'm trying to show here, like for the last 3 years, especially in our group, we have started asking the questions, saying especially how the HPC is moving ahead, how we can take advantage of those technologies, and then trying to accelerate the big data stack. We have, of course, already made several of these stacks available, and our next releases will be the cloud era. distribution. A lot of people are asking for that. We are still tuning and optimizing on that. Our Hadoop for the cloud era, then HBase, we have also started looking at the Impala. And also I indicated like the high-BD benchmarks, MapReduce and RPC will be there. And then this new HDFS, Memcache D burst buffer, non-blocking, those kind of things also will try to push. So let me just quickly summarize here what we see that some of the initial results, what I presented, the results are promising. That means we can really take advantage of the HPC technologies, the RDMA, and especially the file systems, etc. But of course, this is just the beginning. There are a lot of open issues. The open issues are in the upper level architecture. We have not explored that completely. And this is the thing what I motivated. Like if you take, let's say, an old car and you just change your tires, you expect it to run a little bit better, but not completely, all right? The engine is still old. Okay, so that's what is happening. Even though we touch some of the components, we can accelerate it, but we need to totally reevaluate it because the overall architecture was written with slower network in mind, slower network and slower protocols. And now if we can enhance all those things, we'll be able to actually do it much more better. Then these are all the, again, just like yesterday, these are our standard sponsors and these are all my heroes. I always publicly acknowledge their contributions. And the final thing I want to stress here, to bring this community, HPC and big data together, since last year we have started a new workshop called High Performance Big Data Computing. We did it with ICDCS conference last year, and this year it will be held with IPDPS. So we already have there will be a keynote talk by Dr. Chaitanya Baru. He's a NSF program director. We have a very interesting panel already has lined up saying merge or split, mutual influence between big data and HPC techniques. Like should HPC things go to big data or big data should come here, okay? Or how the future will move around. So if some of you are attending or planning to attend IPDPS, I'll strongly encourage you to attend the full day workshop. We also have regular research papers, so it will be a full day event. So with this, let me stop here. If there are any very quick questions, I'll be happy to answer these. Otherwise, we can take some of these discussions offline. Thank you.